Okay, hello everyone. So let's continue our analysis of magnetic circuits, and in the process we have come across a topic called inductance. So let me quickly describe that, and then we'll solve some more problems. Okay. So a few lectures back I was talking about this procedure for solving magnetic circuits, and in that we have seen Ni is R into phi. So the ampere turns are nothing but reluctance multiplied by flux. Okay, so we will start our analysis from this. So I'll write it down. So Ni is nothing but R into flux, okay, reluctance into flux. Now this is very similar to the Ohm's law. Voltage is nothing but resistance into current. So current is analogous to flux, resistance analogous to reluctance, and then EMF is analogous to MMF. Okay. So now I just slightly rewrite this. I'll write it in such that flux is equal to R will come here into I. So you notice that the flux and I are proportional because this is constant. So for a given winding, the number of turns is fixed, and similarly the reluctance is fixed because reluctance depends on the material properties and the geometrical properties, the cross section area and length. So of course by changing the material dynamically you can change the reluctance also dynamically, but then if I fix this, then I and flux are proportional to each other. More current will generate more flux, so is what we understand from this. Now what I want to do is further expand this. So this N is as it is. Now reluctance is nothing but L by mu into A. So this is just substituting the value of reluctance, which is nothing but N mu A divided by L into I. Okay. So again this quantity is constant. Now let's call this as equation 1. Now we know that, so that is rate of change of flux linkages, EMF induced is equal to rate of change of flux linkages. Okay, so what is flux linkages? Now the flux is linking with the turns. Okay, so if you consider some kind of a core and some kind of a turns, let's say N equal to 1000 turns and the current is 2 amperes. So 2 amperes of current is flowing through 1000 turns. So MMF is nothing but 2000 ampere turns. That is resulting in some kind of flux. Now how much flux is generated depends on the reluctance of the ring. Now this flux is linking with again this N. So what is the flux linkages? Is nothing but flux into N. So that is N phi. And what is rate of change of flux linkages? So again d by dt of N phi. But N is a constant, so N into d phi by dt. So this is nothing but EMF induced. Okay. But then let's see because I have this value of phi here, so I can bring this here and then we can find out what it is. Okay. So or what I'll do is I'll take the equation 1, okay, so I'll take it, so I write it here, flux equal to N mu A by L into I. Then I multiply N here and then I square here. So both sides I multiply with N. So N I already have. Then I differentiate it. So N d phi by dt. So because N is constant, I am keeping outside, is equal to, this quantity is constant, so I will keep it as it is, and then di by dt. This is nothing but EMF induced. So I am getting an equation for EMF induced. Now in this quantity n square mu by A, which is constant, is designated or is uh, denoted with the letter L, which is called the inductance of the winding. We will see more why what is the importance of this inductance and how it behaves and all in further videos. Here I just wanted to bring out the mathematical derivation of what is the value of L. So if you know the number of turns, if you know the mu, that is mu naught and mu r, and if you know the area and length of a given coil, you can find out the inductance of the coil. Now another thing is I can once again use equation 1. So let's call this as equation 2. Now again I want to use equation 1 in this. Okay, so what I'll do, I'll just take n and then n mu A by L. Okay, just you see these two are exactly same. I just n square, I just separated this n like this. Okay. So then I multiply I on both sides. Okay. So now this quantity, if you look at equation 1, n mu A by L into I is nothing but flux. Okay. So this whole quantity is flux. So n phi equal to Li. So here you will get another relation. So from this also I can find L is nothing but n phi by I. Okay. So this is also you can find the inductance. If you know the flux linkages and if you know the current, you can find the inductance. Okay. So of course at this stage I have just given two expressions. So this is the first one, this is the one, and this is the one for calculating the inductance. We will see some problems, and later on conceptually also we will see what exactly is inductance. Here I just wanted to bring out the expression for inductance.